Hi, everyone. My name is Sveta, and I'm an algorithm developer in applied materials. And I'm excited to open this session. And we're going to talk today about making a lemonade out of any label, semantic segmentation using noisy annotation. We will go over a few topics. The first one is automatic defect review ADR introduction. I will introduce you our pipeline of defect detection. Then we're gonna I'm gonna talk about the constraints and limitations that we have from our customers, and those things lead us to a different direction in our detection solution. Since the main topic of this meetup is a noisy annotation, so we will refer to weakly supervised semantic segmentation, and we will see a few approaches, and then we will summarize. So before I'll dive to annotation, noise, and our detection solution, I want to refer to chip shortage. I'm not going to talk about the chip shortage itself and not why it happened, but I do want to ask you a question. Who cares about chip shortage? And the answer is that we should care, all of us. The world runs on microchips, and not just the obvious ones in our phones or the computers. And the recent study by Strategy and Analytics claims that 4 billion people own a smartphone, and it's more than half of the entire population. And the first to take a hit was the automotive industry. New cars typically include dozens of microprocessors, and Ford, BMW, and Volkswagen have all reported bottlenecks in manufacturing. So we understand that semiconductor industry have a huge impact on us. And due to that, it's very important to that manufacturing process will tickle like a Swiss clock. In order it will happen, the manufacturing process should be supervised. And here's the big role of applied materials, is that applied materials is a major pillar in semiconductor industry. And our main goal is to confirm that the silicon wafer, the one that is soon going to be microchips, are clean from defects. It leads to our detection, to our defect detection pipeline. When we start from an optical tool, UVision tool, and by that tool we are scanning all the wafer and looking for defective areas. Those defective areas gonna be soon candidates. Then that we are gonna scan them again by high resolution of SAM vision, which based on electrical microscope. And the purpose is to detect and segment the localization of the defects. The final phase is to classify those defects. Now we have different types of defects, and it's very crucial and important to the customers to understand whether the defects that we are catch are critical, and then he needs to stop the product line and to investigate what happened during the manufacturing process, or there are defects that are not that crucial and the customer can repair them. In today's talk, I'm going to concentrate on the detection and the segmentation of the defect. And now we will see an example of a 3D model. You can see here a 3D model of different patterns. Those patterns are going to be printed on the wafers. And here's a simulation of a defect. It's a bridge defect between two lines. It's not supposed to be there. And it also can be detected in our SAM vision tool. Here you can visualize it. So as I said, we have different types of data sets with different backgrounds, and also different types of defects, big defects, small defects, medium one, with low SNR. And one of our detection solution is supervised detection. So we have our input data is basically we have a pair of images. Sorry, pair of images where one of the images is a defect image, where you can see here in a green color the annotation of the defect, and its pair is a reference image, where the reference image basically having the same pattern as a defect image, but it's clean from defect. And where the input to our network is this pairs, where the network also can utilize the information that we are entering it when we're using also a reference image. So our solution based on UNet, where we have the encoder and the decoder, and of course also skip connections. And in our solution, we have a customized loss. I will relate to that further in my talk, where of course we have a mask, which is a ground truth that are coming from our from the annotators, and of course we have a grade map where it's a probability for every pixel to be a defect. Now, before I'm gonna say more details about our solution, I want to refer to the supervised detection, or in our case, it's a supervised segmentation. So when we're talking about supervised detection, where the optimal scenario is to have a lot of images, a lot of defects in our case, and a very accurate and tight annotations. So this leads me to our annotation procedure. I want to share it with you and to connect you to the way that our customers are annotating the data. So our customers having those experts that know what kind of defects they are looking, what types of defects they might occur during the manufacturing of the wafers, and they get in a defect image, as you can see here, and also a reference image. The reference image helps to the annotators to understand whether we have some any anomaly in the defect image, or maybe we don't have there any defect at all. So since our annotators are human, so it's a natural thing to do mistakes, right? And if it's different annotators, it also can lead to inconsistency in the labels. This is the first noise that we have in our labels. And additional thing is, because the defects might be very small and with low SNR, so not always we can really visualize them, or maybe they're not so, as I said, with very low SNR, so we might miss these annotations. So even before we're gonna think of like what kind of architecture we need to use, or what kind of loss we need to use, we already suffer from a human mistake, a natural mistake, and it's the noises that we have in our labels. So a few examples of our data sets. We have a lot of data sets, and I'm not trying to hypnotize you here with this pattern, with repetitive pattern, but here is an example of two defects. You can see here a bridge defect with its annotation, and you can see here a cut defect where you have a cut between two lines. Here's the reference image. This is the way it should look. Okay, another data set, we have a different pattern, and you can see here a big defect. I can say maybe a medium and between medium and a big defect. Now, in order to understand what exactly the defect here, we have a reference image, and our annotators can also get a difference image where then we can visualize that these edges are really defected. This is the defect itself. But pay attention that the annotation is bigger than the defect itself. So part of the areas here is the background. So additional noise that we have here. Now, pay attention to these small ones. It's also annotated, but if we will see in the difference image, we can't really see them. So it also might be a mistake that some annotators for some reason annotated them, and this is the data that we get in order to train after that our model. So I showed this slide to my friend, to my coworker, and he said to me, come on, this is what you show them? Like, it seems so easy. Like, why we even need a neural network to solve these problems? So I promised to him that I will emphasize in this slide that this is the information and the data that I can show you, that I can share with you. But you have to believe me that there's different backgrounds and very complicated patterns in our data sets. And of course, a lot of different types of defects. As I said, they can be with amorphic structures and with low SNR. And this is the complex data sets that we have. In addition, our data set is imbalanced, meaning that we have different types and we have different amount of data for every class. So it's also an issue when we are training our segmentation model. So our customer requirements, we saw one problem is this annotation, but this problem is emphasized when we also have customer requirements. And we will start from the annotation budget. The annotation budget is limited to 500 images. So basically, the annotators can label for us only 500 images. So here's a challenge for you. If our data set consists of thousands or even tens of thousands of samples, we need to sample. And remember, our data also is imbalanced, and we need to sample and to pick those informative samples or defects that should represent all the data sets. So it's not an easy task, believe me, because I'm working on this project and it's very challenging. So you can think about it. It's really a problem. And the annotation time is limited also to 2 hours. So there's always, it's a compromise between to get a tight annotations, which we know they are better, but we also want to have a lot of label data. In our case, it's only 500. So we are taking what we can, and this is a loose annotation, the ellipses that I show you in previous slide. Sorry. Our training time is also limited to 2 hours. So segmentation solution will take only 2 hours. And the performance, we need to reach performance of recall 0.95 and precision 0.8. So we're giving a higher weight to a recall, and the reason for that think about mass production. When we have some defect, the crucial and critical defect in our microchips. Since we're talking about mass production, so we're talking about a lot of microchips that will suffer from this defect and might be just useless. All the entire microchips can go like we can't really use them, and it costs not only a lot of time that was wasted on the manufacturing them, but also tons of money. So we give, as I said, give a higher weight to the recall. So the combination between the annotation issue with the customer's requirements leads us to specific data that we can use for our solution. Like what exactly we have in our basket, in order to solve this segmentation problem to detect our defects. So we start from images. You saw the examples of images that we have a defect image and reference image. We also have annotation, our ground truths that are loose and they're ellipses. And we have additional data that we can utilize. One of them is image level label. Image level label is basically a classes. So we can have a binary class, which means if we have a defect in our defect image, we consider it as a defect class. And if we don't have a defect in our defect image, because remember that I said that we are scanning a candidate's area. We're not promised that we'll see there a defect, and there are scenarios that we don't see a real defect in the defect image, and then we can cluster them as non-defect. This is one set of image level information that we can get. Another information that we can get from our customers, if they're willing to share it with us, is multi-class, meaning that, as I said, we have different types of defect class, and if the customers can share with us the defect class, so we can also use it in order to improve our annotations. So basically, our solution is not really supervised segmentation, because we have this noise that we're talking about. Our solution is more weakly supervised segmentation, and I want to show you the approaches that we can take in order to overcome this obstacle. So one of the approaches is annotation refinement. So we can use image level label. As I said, we can get this information for the solution, and also there are classical algorithms that we can apply and to refine the annotation. Combination of both of them is also a possibility. And there's another way to tackle this problem of noisy annotation, is not only to refine our input, but during the training procedure, we can have a modified loss. In our case, our solution, we have a customized loss, which is it's a weighted loss based on noise model. And I will try to elaborate about it more in the final slides. And then, of course, we can combine both of the solutions. None of them is giving us a final solution, but the combination can give us a closed solution. So since I can't really talk about or reveal too much data about our solution and the way that we are gonna tackle exactly our problem, we chose to show it through papers. As every CNF and the project that we start, in this case we are continuing this project. So we're doing, of course, paper review. We want to see what is common solution, what are the new solutions that we can that we might adapt to get new ideas. Of course, we want to stay updated, and this is the way that I want to connect you to the way that we are going to develop our next steps in order to finalize our detection solution. So we will start. So as we understand, we are talking here about weakly supervised semantic segmentation, and we will start from box level label to pixel level label. So we have in here these rectangles of annotations during the training, and in the test time, we want to get a segmentation map. It's very similar to what we have. Instead of rectangles, we are having ellipses. And in the next approach, we can use image level label to pixel level label, meaning that we have classes in our image during the training, and then in the test time we want to get a segmentation map. So we'll start covering this approach since the annotations are already closer to the segmentation. This is the final solution that we want to get. And I want to talk about this paper from CVPR 2017, that talks about a solution that during the solution that they propose, that during the training, they don't need to change any training procedure during the training of segmentation map. But this solution is in iterative solution, and I will explain and I will elaborate about it. Just let's start from the input image. This is the ground truth, and this is the box, the noisy annotation. And what they claim that once we're training our segmentation model with this initial state, after the one round of training, we can take the results and we can replace our ground truth with the results, and then to train again and again, and to do it iteratively. They claim that after 10 rounds, they get pretty good results. The problem with this solution is that in our case, we're limited to 2 hours, and to do 2 rounds of training, like 20 hours, it's not a really feasible solution for us. But there's another thing that they suggest. Let's take the box and create and modify it to a different initial state using GradCut Plus, which is iterative algorithm-based GraphCut, and MCG, multi-scale combinatorial grouping. Using both of this algorithm in order to refine the annotation, we won't need any iterative solution. And here is what they show, that x-axis is a training round, and y-axis is intersection over union. The green curve show us when we start from a rectangle and we are training 10 rounds. You can see that here the convergence of their solution, of the iterative solution. You can see the big gaps that the big gap that you still have between the fully supervised. And once you start from a better initial state after using those algorithms, so you're already converged after 1 round of training, and the gap is smaller than the first solution. So it definitely seems like something easy that we can try, try to see whether it helps us with our annotations. So the advantages of this approach, that what they claim in the paper, that it's maintained segmentation training procedure, but the disadvantages for our cases, because since we're having also small defects with low SNR, so it might filter out defects, and it's something that we need to check. An additional thing is regarding the parameters tuning. So in our data sets, we want to have the same parameters for the algorithm, obviously, and it's not possible to manually tuning them all the time. And to develop something automatically, it might be a little bit complex, so something we need to think about. The next approach is, the paper is from CVPR 2021, and this solution consists of 2 parts. The first part is using classification network in order to get a new and improved mask for segmentation network, and the last phase is to train a segmentation network with some modified loss. So let me explain quickly about this approach. It's not a classical classification network, because what they do here is they use a classification, like the classes of the object, but they also use the annotations, the rectangular annotations, when they train the network. And the reason why they're doing that is they train here not the classification network is not for L classes, like the L object, the types of object. It's L+1. The +1 is the class of a background. So this classification network needs like to concentrate or to distinguish between the classes, which is a foreground classes, and the background class. And the way they do that is they using feature maps from the feature extractor. Of course, they also have the mask, and all the pixels out of the box is considered to be a prototypical features of the background. Once they have it, when they calculate them, they do a constant similarity between the prototypical features and the feature maps, and this is in order to get attention map for every channel. After the averaging, they have an attention map for the background. So pay attention that here the high values, this is the red values, represent the background, and you already can see that in the boxes you can see the object themselves, like it's in some way cleaned the rectangle and leave the objects. So now we can use it, and by one minus attention map of the background, we can use attention map for the object themselves, and to calculate the prototypical features for the objects. Now they train the classification network, as I said, to L+1 classes, and after the training, they want to get masks for the segmentation network. The way that they're doing that is they're using background attention map, what they can calculate using this the classification network, and they also use CAMs, which is class activation maps. Together, class activation map for every class, and then together with like 3 of them here, they use then CRF, and they're getting a new mask for segmentation. But it's not a real ground truth, like it's not a real mask like typed mask. So now they want to have another candidate of the mask, and I will explain later why they really want that. They use this mask and they extract prototypical features using, again, feature maps, but the prototypical features of the classes, they calculate correlation maps for every class. After argmask, they get another mask. Now what they do, they start to train their segmentation network. And the way that they train that they want to have a confidence areas for every class, meaning when those 2 masks are agreed, it's a confident area for a specific class. Where they don't agree, it's a weakly confidence area. And they utilize this information and use it for their loss. Their loss consists of 2 losses of confidence areas and weakly confidence. The confidence areas, they just use a cross entropy, and for non-confidence area, sorry, they calculate a confidence map for those pixels. This confidence map is constantly changing during training. Okay, and this is how they train their segmentation solution. And we can see that for example, if this is the input, the ours, it means they, the authors, of course, this is the combination of 2 masks that coming from the classification network, And the gray areas is the unconfident areas. The purple is the confidence areas. And if we want to see how the confidence map look, it changes during the training, and it's modified and improves. So in this paper, they tackle the annotation problem from both of, like, let's refine the annotation by classification network, because we're having a image level image level information, and also during the segmentation training. Okay, now I want to relate to our solution, and then I will finalize everything. So our solution, you already saw it. This is the inputs. We have in a unit, and we have our own customized data loss. So the data loss consists of two expressions, where each expression is a function of cross entropy. And let's say, for example, we're looking at the foreground loss. We're not taking all pixels of the foreground loss. We're not taking all the pixels of the defect for the foreground loss. We have some logic behind this, and we also, like in the previous method, we also calculate confidence areas of the foreground and the background. We do it differently than I showed you, okay? And it's not modified during our training, and this might be a gap that we are having. But the logic is, since we know that our annotations are noisy, so part of the area in the annotation will be, of course, background, and part of it will be a defect. So we need in some way to give a different weight to the pixels inside the defect and also outside the annotation. So I just can't reveal everything, but what I can say to you that in this solution is already proved itself, since in most of our data sets we reach our spec performance, as I showed you before. In complex data sets, we still have a gap. We have a slight gap, but we need to improve. And the reason that I showed you the different approaches and the papers is, since this project is under development, and we are adapting part of the things that I already showed you also to our solution. So I want to summarize and to say that it was very important to us to take the issue of noisy annotations, and in our case is we deal with defects, and the other cases like medical images, the annotation of the tumor is very crucial. In automotive industry, it is important to know what obstacles can be on the road, meaning that this problem concerns all industries, the one that want to develop a segmentation solution. And wanted to show you what things and approaches can be taken in order to overcome this obstacle. And if we will summarize what we saw until now, so one of the approaches is just annotation refinement, and it can be done by classical approaches. It might be fast implemented, but in our case, we can filter out defects. So it's a problem. But you can think maybe in your cases it's not an issue. And the other solution is based on classification network. So the thing is that if we want to train classification network, it takes, of course, also time. In our case, we're limited to 2 hours, so we need to understand how we are dividing the time between the classification network and the segmentation network. And also the development of classification network itself, we need to understand whether we can also have an explainability, or to understand what it does behind the scene in order to do this refinement of annotations. when we understand that this solution is not optimal, and there's another way to tackle this process by loss modification, it might be fast when we can test different losses and see what helps us or not. Not always you can explain why the network behaves in a certain way because of our loss. And again, this solution is not optimal. So in our practice, it's a good one. It's better to ensemble both of the solutions. And we're definitely gonna try the approaches that I showed you before, and to close the gap that we are having in our solution. Anyway, thanks for listening. And if you have any questions, we will have a Q&A section at the end of the meetup, and you can reach us and contact us with these details that I leave here. Thank you very much.
Hi, everyone. My name is Shira Mir, and today we'll be discussing leveraging pre-trained transformers for part co-segmentation. And this work I actually did during my thesis. I'm a graduate student under the advisory of Tali Dekel in the Weizmann Institute of Science. And this work could not have been done without our amazing collaborators, Yossi Gandelsman and Shai Bagon. Okay, so as most of you probably know, transformers have been quite ubiquitous within the NLP domain and have slowly taken over the computer vision domain as well, as you can see in this graph. And just as a brief summarization, let's go over the VAT architecture, vision transformer, which is one of the most common transformers used in computer vision. So we begin with an image. We split it into several non-overlapping patches, small patches. Then these patches are passed through linear projection, and we receive an embedding, a vector representing each one of the patches. Then, in order to avoid the transformer from being a permutation invariant, we add positional embeddings to each one of the tokens in order to make each one of the tokens understand to which position did it belong in the original image. We also have a learned class token, which serves as some type of global representation for the entire image. All of these input tokens together are passed through a transformer composed of L transformer layers. And finally, this is the class tokens embedding from the transformer is passed to through an MLP and provides us softmax of different classes. And this entire vision transformer, VAT, is thus trained in a supervised manner. Now, the interesting thing, one of the interesting things of this architecture with respect to convolutional neural networks is the fact that it preserves spatial dimensions. So as you can see, all of the amount of arrows, the amount of tokens per se, remain the same through the entire architecture up until the final layer. So actually, assume we have some pre-trained CNN that someone trained, say, on ImageNet in a supervised manner, we can receive deep features representing a specific image, but they will have a poor resolution, a coarse resolution. They would be of low granularity. On the other hand, if we take a pre-trained VAT, because it maintains the resolution of the images all through the layers, then we will receive both high resolution or high granularity features, and also these features will be semantic. So just one more thing about these VATs. At the beginning, we saw VAT, which is trained in a supervised manner, but these VATs can also be trained in other ways, such as with a self-supervised loss. And in this lecture in particular, we will use dyno-trained VAT in order to do part co-segmentation. So whenever we say Dino VAT, we actually mean a VAT which was trained with a self-supervised loss without any classes on the ImageNet without regarding the labels. And actually, in the original Dino VAT paper, they already showed that the intermediate features within these models can produce quite meaningful saliency maps. So you see in each one of these images, the highlighted area corresponds to a dominant object in the image. And afterwards, a few works came out that already used these features for some coerced tasks that need coerced semantic representations. For instance, for object discovery or for coerced segmentation, you see the quality of this segmentation is relatively poor. You could see artifacts over here, grid artifacts. And in our work, we did several contributions. First of all, we created dense visual descriptors out of these VAT features. And we also discovered that VAT features of a VAT pre-trained with Dino in a self-supervised manner are shared among classes and distinguish object parts. And in fact, this observation of the signal within the Dino VAT is so powerful that we actually managed to take the descriptors we created out of the VAT features, and with only using lightweight methods, we were able to actually solve 3 tasks: co-segmentation, part co-segmentation, and semantic point correspondences. And we even received state-of-the-art results on the part co-segmentation task. So in a nutshell, by creating dense descriptors from these VAT features, we actually figured out they are very well suited for co-segmentation and part co-segmentation tasks. And again, this is quite interesting because the methods that we used on top of these features are very lightweight, so that they don't involve extra learning nor fine-tuning. So this is what we will see later on in the presentation. So first, let's begin with how do we actually create dense descriptors, right? So in the VAT architecture, we've seen that an image is taken and split into non-overlapping patches. So it's split into some sort of grid in a specific resolution of a specific patch size. And now let's see the similarity between the descriptor in this location of this patch to all of the other descriptors in the image. This is what we see over here. So as you can see, the descriptors are pretty semantic. So a descriptor that belongs to an ear actually also highlights on the other descriptors that belong to ears, and it fires less on the face and even less on the background. And over here, we're actually doing the sampling of the descriptors from non-overlapping patches. But what we discovered is that if at test time, without retraining, we interpolate the positional embedding and actually sample overlapping patches. So instead of dividing the image into non-overlapping patches, we divided it into overlapping patches. We received descriptors of even higher granularity, but they still maintain their semantic properties. So you see that this map is of higher granularity, of higher resolution, but it still maintains the semantic properties. And this can be done further and further until we reach near pixel resolution. So this actually enables us to get dense descriptors from this pre-trained transformers with a trick that's done in inference time. So as you can see, as we've seen before, if we pass an image through a CNN, we receive a coarse representation, but if we pass it through a VAT, we receive a very fine representation. And in fact, you can think about it this way. If we have a representation that is both spatially localized and has high resolution, but is also semantic, this actually makes object parts emerge. So as you can see over here, descriptors that belong to specific parts, such as the ears or the eyes or the mouth, kind of seem more like each other. And this is a very strong property that we later use to do the part co-segmentation and co-segmentation. And maybe to finally convince you that this signal of object parts exists within the VAT, the Dino VAT, within the Dino VAT architecture, then, okay, so first of all, let's just examine the fact that this is common across classes. So as you can see, this is the representation for a specific dog. And you see that the ears are colored light blue, the eyes are colored red, and the mouth is colored pink. But if we do the same thing, the same PCA analysis on the descriptors for the other images as well, we can see a consistency of the different object parts across images from different classes. So regardless of whether we're looking at a wolf or a dog or a lion or a tiger or a cat, we have descriptors, we have similar descriptors in the region of the ears, in the region of the eyes, of the mouth, etc. So we discovered that these descriptors are not only semantic and not only distinguish parts, but they also are shared among common classes. And this makes sense because the VAT that we're using is actually self-supervised. So it never even had the notion of different classes before. No one told it explicitly to differentiate between a cat and a dog. It just saw images and it used its training objective on them. Now, in order to be fully convinced that this signal of localizing parts exists in pre-trained Dino VAT, let's look at the following demonstration. So what we did is we took images from the Pascal parts dataset, which have ground truth annotated object parts. And as you can see, the objects are common, but the classes of the images are not common. So we have sheep, we have horses, we have cats, etc. And what we did is, first of all, we took the descriptors of all these images and we applied TSNE upon them. And what you see over here, each point represents a descriptor from one of the images. The color of the point represents the ground truth part it belongs to, and the shape of the point represents the class it belongs to. So as you can see, a supervised VAT kind of separates these representations according to class. So all of the representations that belong to, say, the cat that have a shape of a circle belong to a common area in the TSNE. On the other hand, all the representations that belong to dogs go to a different area, etc., etc. But if we use a self-supervised VAT that didn't have an explicit notion of what a cat and a dog is and that the fact that they should be different from each other, then the TSNE actually separates the different parts. So you see all of the tails, for instance, regardless of the shape of the point, regardless of the class it belongs to, all of them get clustered together. The same for all of the legs and all of the torsos, etc., etc. So this kind of demonstration convinced us that the signal does exist in the pre-trained VAT, and then we went on to leverage it for practical application. So now let's take a look at the simple method we used upon these powerful features in order to apply both co-segmentation and part co-segmentation in a single pipeline. So what we did is we took a collection of images. The collection could be small, big, it doesn't matter. We extract the Dino VAT features for all of the images, and then we receive both our dense descriptors that we saw earlier and saliency maps, similar to those shown in the original Dino paper that we saw in the beginning of the presentation. Then we simply apply k-means on all of these features together, and because the different descriptors are gathered among parts, so we have a relatively coarse separation of the different object parts and the different backgrounds. Then we use the saliency map in order to decide which one of these clusters belongs to the foreground and to the background. So for each one of the images, we have a saliency map, and each one of the images votes whether each one of its segments belongs to foreground or background. And assuming that the segments are indeed consistent among the images, we finally get only the foreground clusters that are foreground in most of the images as our co-segmentation maps. So what this algorithm so far is able to do is, given a few images, it manages to co-segment the common objects. Then in the next stage, we only take the descriptors from the object regions that we discovered in this stage, and we reapply k-means on them. So now we only apply k-means on the regions marked over here. And then, as we've seen before, we receive the different object parts. And what's nice about this work is that the object parts are indeed consistent across different animals. And this is done in a completely unsupervised manner. So both the pre-trained model and our lightweight method are completely unsupervised. And now let's take a look at a few results. So here you can see results from the MSRC dataset that only include images from a single class, but we still see pretty impressive segmentation. It even manages to capture the cow that is behind the main cow of the image, the cow that is less salient. And now let's look at a few part co-segmentation results. So here we can see part co-segmentation on the AFHQ dataset, which is actually consists of 1,500 images. And here we only show a few of them. And as you can see, despite the varying of the appearance of the different images, we can still see consistency across the classes. So there is a single class that evidently belongs to all the ears. There is a class that belongs to all the foreheads here in blue, a class that belongs to the nozzles, the eyes, the whiskers. And to the best of our knowledge, this is actually the first method that is able to produce part co-segmentation in a way that is consistent across classes. We also, one of the case studies that we experimented with was human faces, right? Because in ImageNet, we don't really have a class, we don't really have any class of humans, but we do have a lot of images that contain humans. So we wondered if the ImageNet dataset is strong enough to give us plausible results on humans as well. And as you can see, this appears as true. So we have nice separation of the eyes, of the nose region, the mouth, the chin, the cheeks, the ears, and it's consistent across different humans. Then we wanted to try and take this demonstration to the extreme. So instead of applying co-segmentation on a lot of images, we wanted to apply co-segmentation on images that both vary a lot in appearance and also are only consist of a pair of images. So this is a pretty challenging scenario. And as you can see, we managed to get quite interesting results on these scenarios as well, even though the classes are quite arbitrary, right? We don't have a data set for part segmentations of shoes, yet our method in an unsupervised manner enables to get part co-segmentation of the shoes. So we have this region of the shoe, which is common, the green region, and also the laces, similarly in the animals. So since both of these animals have horns in common, the method decided to give the horn an entire cluster, and also in the cases of bottles. So we're able to separate the logo of the bottle and the different parts of the bottles. And this is, again, all done without any training or fine-tuning, only using simple and lightweight methods. It also runs pretty fast. Then we decided to take this even to the next level. So we said, if we're applying our method on a collection of images, why can't we just apply it on a collection of frames? In the original Dino paper, they showed that the Dino VAT features are consistent across image frames, across video frames. So we decided to apply our lightweight methods on videos as well. And as you can see, we received part co-segmentation that is consistent across the video. And this is a quite interesting demonstration as well. And the parts are pretty much consistent across the video. Oh, sorry. And despite the fact that today's lecture is mostly on co-segmentation and part co-segmentation, we also wanted to give you a little sneak peek on the last application, which is correspondences. So what we did in this application is we took two images of either same or different classes. So Here it's a same class scenario, here it's a different class scenario. And what we did is in an unsupervised manner, the user only says the number of correspondences it wants to find between the images, and then the method automatically finds such correspondences that cover as much of the objects as possible and also are semantically meaningful. So over here, for instance, you see that the beaks have a correspondence between them because it's an interesting region and also a semantic region. Also the tails, also the legs. And this is impressive because this method works quite nicely even on cases where the appearance is very different. And the reason this works is because of the Dino VAT representations being invariant to different classes, but being shared among object parts. And if we compare ourselves to a recent CNN-based method named Neural Best Buddies, you can see that we perform much better. So here, for instance, the entire region of the wing is mapped to the region of the head, which is a wrong semantic correspondences. Or here, for instance, this green dot doesn't match the wheel, it matches some sticker over here. To conclude, Dino VAT features, as we see them, are especially powerful for several scenarios. So first of all, for the scenarios where we have absolutely no labels at all, for an unsupervised scenario. Secondly, for scenarios where we want to receive part co-segmentation. So not necessarily to co-segment an entire object or to segment an entire object, because there are a lot of works that do this, but rather to focus on part levels. We also, usually the data sets that do part level annotations are way more scarce. So this method is actually going to shine in this scenario where we lack labels. And also for scenarios where we want to operate on data sets that don't necessarily consist of images from a single class, but rather from several classes, several close classes that have similar parts, but are not necessarily exactly the same class. Another thing I wanted to emphasize in this conclusion is that zero-shot methods are quite underrated. So we have many papers nowadays that train very large models and show that they're able to improve state of the art. But what we want to offer in this work is to actually take a pre-trained model that someone else has already trained and to distill, to identify the exact properties that it has and other models don't have. And then once we identify these properties, we know for which tasks it's going to shine. So here in this model, we discovered that the Dino VAT has a very strong signal of object parts. So for that reason, it was quite easy. We could use a quite lightweight method to solve part co-segmentation with it. And also in the sense of sustainability and being more environmentally friendly. So using a pre-trained model for specific tasks is also better than to train a model from scratch by ourselves. And finally, the last remark is that removing human supervision can lead to quite wonderful places. So as we've seen in the TISNI demonstration, the supervised VAT didn't distinguish between object parts, but the unsupervised VAT, the self-supervised VAT, did. So maybe using more self-supervised methods or self-supervised models will uncover signals that are quite useful to us as humans, even though we didn't explicitly guide these models with any human supervision. That's it. Thank you for listening. And if you'd have any questions, I'll be happy to take them.
So good evening, everyone. My name is Eitan Kusuto. I'm an algorithm developer at Trax Retail. And today I'm going to be speaking about finding nothing with segmentation. So this is a joint work with Paul Yudkin, Kobi Maron, Yochai Dvir, and Itzik Levy. So a little bit about me. So I've got a BSc in engineering. I'm a graduate of the ITC Data Science Bootcamp. If you haven't told by the accents, I'm born and raised in South Africa, and I've been in Israel for around 5 years now. So a bit about Trax. So Trax Retail at its core uses computer vision to recognize products in retail stores at scale. And we provide this at a very high recognition accuracy. And our customers use this product level visibility to help inform them make smart actions in store, and also provide insights and intelligence for decision makers. So just some numbers. So we recognize around 1 billion products on a monthly basis and digitize around 1.5 million stores on a monthly basis. And we do it at recognition accuracy of 95%. So before moving on to the project itself, I thought I'd talk a little bit about data annotation at Trax. So data annotation at Trax is basically split up into two streams, with one team generating the bounding boxes and the other team providing the labels for those bounding boxes. The labelers, which we also call voters, are able to vote on what the label should be. And if there is a general consensus, then the label is given. However, it could be that different labels are given by each voter, and then we don't have a consensus, and this results in an inconclusive tag. As you can imagine, this can result in quite noisy data, and down the line, it can cause issues when training and evaluating the model, even though it's a very rare occurrence. So what is the motivation for this project? The motivation of this project, as I said before, is to detect nothing. So it's literally that, detecting empty spaces on the shelf. The reason being that this is of interest to our customers because it helps them make quick decisions in store. For example, if a product on the shelf has gone out of stock, they can receive an alert that, the product's got out of stock, you better go and replace it. And this, reduces the loss of sales in the store. So this is a typical image that we would see in our ground truth data. The red bounding boxes represent products. The blue represents empty, and the green represent the inconclusive tags, which I spoke of before. So while we're looking at the data, with empty, it doesn't happen very often in reality. So that results in data scarcity for this class. In addition, we have quite high variance in the empty bounding boxes because empty spaces can change in dimensions all the time. So this presents various different issues as well. So this is a meetup about segmentation. So you may ask yourself, why not simply train an object detector to detect these empty spaces? And the answer is that we tried, and it didn't have good performance. The reason being, number one, we have the scarcity in data and high variance, but also the network confuses empty spaces with other places in the store, such as the ceiling or the floor. And so this made it impossible to train a production grade model. So how did we solve this issue? Well, our first idea was, we said, you know what, if the empty detector, object detector, places these bounding boxes on the ceiling, on the floor, we can use an in-house model to clean it up. Now, this in-house model is a segmentation model. It's called ROI, region of interest. And essentially what this model does is it's trained to output segmentation maps of regions of interest or where we think there are products on the shelf. And we can use this data to remove anomalous tags like the ones I mentioned before. So for example, in this case, you can see that the detector placed bounding boxes on the banner above here, and also to the right. And these are anomalous tags which we want to get rid of. So using the ROI model, we are able to clean up those tags. So the next question is, why not, is there a way to combine this ROI model with the detection of empty? Why have two models when you can have one? And so we thought it was a natural approach to simply add the task of detecting empty to the ROI model, since intrinsically the ROI model is trying to reduce these anomalous tags. And in addition, multitask training has shown to improve both in the individual tasks on their own as well. So the ROI model is based on a unit architecture. You've already seen it in this meetup. I'm not surprised. Anyone who deals with segmentation probably knows this architecture. It consists of a down stack and up stack, and we have these connections which connect each layer of the down stack and the up stack in order to improve the performance. And so we simply, to add the empty detection task, we just added an extra output to this network. So we had one head, which was responsible for detecting ROI, so where the products were. And we had another head, which was responsible for detecting where we had empty spaces. Okay, so moving on. So this would be a general input output of an ROI. So we can see the ROI is able to output where there are products on the shelf. And in practice, we can remove those anomalous tags based on that information. So looking at what we'd want for our empty detector is something like this. So clearly these empty spaces in the middle, we want to detect as foreground in green and the rest in background. So just putting everything together. So what are the problems we're trying to solve here? So number one, we're trying to detect empty spaces. In addition, we have to deal with various data issues. So because this doesn't happen, there aren't many empties in reality, so we have a small sample size. This results as well in an imbalanced data set. And furthermore, we have noisy data as a result of the inconclusive tags I spoke about in the beginning of the presentation. So I'm not going to go into too much detail, but segmentation is essentially classification on a pixel level. And it can be broken up into semantic segmentation and instance segmentation. In our case, it's simply semantic segmentation. Okay, so how do we do it? So this shows our first training with the additional empty head. And you can see that there's terrible overfitting here. The orange represents the training accuracy and the blue represents the validation accuracy. Our hypothesis was that because we were using a very heavy model with 40 million parameters, that this was the reason for overfitting. In addition to this, it was quite an old model and needed some sprucing up. And so the decision was to use a new one. And I decided to go with a very lightweight model. It was actually a model which I found in a blog post by Francois Cholet, the mastermind of Keras at Google. And essentially, it's a unit-ish network because it doesn't have the connections between the upstack and the downstack like the original unit. However, it's replaced with dense connections or skip connections between each layer throughout the downstack and the upstack layers. And in addition to this, it uses separable 2D convolutions in order to reduce the parameter count. And so it reduces down to 2 million. So we trained, and what do you know? Still overfitting. So we decided to add some regularization. So let's sprinkle some dropouts. So with 10% dropouts, we can see that there was a minor improvement in the overfitting, but still not good. So we added additional regularization. In this case, L2 regularization in the convolutional layers, and increased dropout to 20%. And as you can see, we were able to reduce the overfitting substantially. However, now we had an issue of underfitting model. So in order to account for this, we increased the capacity of the model by increasing the model width. We did this by simply adding the number of filters that we have per layer in the model. And we found that this indeed helped reduce the underfitting of the model. However, specifically for the empty head, we found that it was still not, it still didn't have good performance. So we specifically added an extra convolutional block on the empty head in order to increase the capacity there. And we found that it did increase the performance of the empty. However, we're still not at production grade. So we went back to the data. And as I mentioned before, we have an imbalanced data set. So we thought a weighted loss would be a good solution for this. So it's simple, no architectural changes, it's configurable. And the way that we did this was simply to understand what the ratio of imbalance is. So for example, if we have 3 products for every empty, so we have a multiplier of 3 on the empty head for our loss. However, we found that it didn't work. It penalized the entire model and in fact degraded the performance of the original ROI head, which was unacceptable. So just an interesting note here. You can see that there's this trade-off between the empty head and the ROI head. And it's very clear that this loss multiplier gave a bias to the network to improve specifically on the empty while degrading the ROI head. So we removed the weighted loss and again, went back to the data. And all we did now was simply oversample our training data set such that at least 50% of it contained images with empty spaces. And this really was a breakthrough in our research. And this is what got us very close to a production grade model. However, it still was not there. So we went even deeper into the data. And what we found are confusions in our ground truth. So these inconclusive tags, which I spoke about before, in some cases, they were on empty spaces. The problem is that our model didn't distinguish between real empty spaces and these inconclusive tags. And garbage in, garbage out, so we weren't able to reach that production grade performance. So in order to deal with this, we simply removed these the effect of these pixels in the calculation of our loss during training. And this reduced the effect of these noisy labels in our training. Okay, so if we look at the final architecture, so we have a Cholet UNet-ish kind of network, and with more filters, so a wider network, and we have the extra convolutional block for the empty head. Okay, so the question, so now that we have a model which is able to produce segmentation maps for both ROI and for empty, the question is, how do we use this information? So specifically for empty, we needed to convert these segmentation maps for empty to bounding boxes, because that is what our reporting layer knows how to use. So how do we convert these segmentation maps to bounding boxes? So first, we create a binary segmentation map based on the segmentation map that we have, and that's based on a confidence threshold. And once we have that boundary segmentation map, we can then generate a polygon on the bounds of that of where we think there is empty. And then based on that polygon, we can then generate a bounding box, which represents the area where we think there is empty. However, we want to produce more realistic bounding box sizes for empty. So what we did was simply calculate the average bounding box size in the image. And based on that, we split up that bigger bounding box into smaller, more realistic bounding boxes for the empty class. Okay, so in summary, we added empty detection to the original ROI model, and we did it without degrading ROI performance. We dealt with imbalanced data by using oversampling, and reduced the influence of noisy data by specifically dealing with it in the loss function. And since we started off with a lightweight model, we were able to iteratively add model capacity such that at the end we had the optimum model for multitask, which was lightweight yet high performing. And of course, after some testing, we're able to deploy this at scale and delight our customers with accurate insights. Also, we're hiring. If you're interested, please have a look at our website.
And that's it.
Okay.
Can you see the first question, Sheila?
Yeah, now I can see them, so I'll just read it out loud.
Yeah.
Do you
perfect.
still feed all the overlapping patches into the same forward path, or do you do a running window of the entire image with 1 pixel offset each time? And if the first option, doesn't that make the memory requirement crazy? So Dan, these are actually really great questions. So in the process of doing this research, we actually tried both options, and they both work quite nicely. We found the first option, the one where we feed all of the overlapping patches together, to be more effective. But in practice, we found that the other option works quite well as well. Indeed, it requires more memory. So if we use the first option, then the method is limited to like relatively small size images, not too small, I guess 200, 300, 400 pixels top, but not high-res images. And the other option, indeed, to do the running window option enables us to run also on high-resolution images, but then the running time is what you compromise for. And in this work, we wanted to put an emphasis more on doing lightweight methods that are relatively fast. So that, and also we saw that inducing all of the overlapping patches together was slightly better. So that's what we chose eventually. But they both work quite nicely. The other question is, have you tried testing the Dino VAT also on grayscale images? Would it work for those cases, in my opinion? Okay, also a good question, because I have something interesting to say about it. So actually, I really recommend all of you that were interested in my work to also read the original Dino paper. It's very interesting, and they show a bunch of cool stuff. And actually, if you look at the nitty-gritty details of how the Dino VAT was trained, so you see that they used a bunch of augmentations on the images in their self-supervised loss. And one of the augmentations was to adjust color. So what intuitively it means to use this type of augmentation within the training process is that the representation will be invariant to it. So intuitively, we can say that any augmentation that was used in the Dino pre-training, we should be invariant to. And in practice, I also tried it on grayscale images and received nice results. But I assume if someone would train a Dino VAT without such augmentations, then grayscale images might be a problem. Also, ImageNet does contain some grayscale images, so there's also the dataset bias that should help working on grayscale images. Last question I see, should VIT be pre-trained on similar domain images, i.e. the same way as we need for transfer learning? I'm not sure I fully understand the question. I can say a few words on the limitations of this method. So I showed a bunch of nice figures where we have nice results, but it's not magic, right? Dino VAT was trained on ImageNet. So the type of signal, the type of images it can work on should be relatively close to ImageNet, to the type of data we have in ImageNet. I think it could be interesting to try and use our method on medical imaging. I've also heard there are some attempts, but generally I'm quite confident to say that it will work on images that match the ImageNet distribution. So animals, cars, vehicles of sorts, clothing, apparel, natural images in general. These are the domains where it works best. But I think intuitively I would say I assume it will have surprising generalization capabilities because of all the augmentations that were used in the model training. But this is not part of the work that they showed. So maybe an interesting further direction. Thank you. Anyone else?
You have another question from Ophir, assuming you know. Yeah. So in the meantime, you can ask questions, all our speakers, write in the chat, feel free. So yeah, I can answer this one.
Okay, so assuming you know that some space is empty, can you know with some confidence? This is not, I don't think Ophir's question is for my work. I think it's for Eitan. So, and thank you Yael, for the
So
comment.
Eitan, the stage is yours.
The answer is yes, but I can't go into that.
It was, okay, Ophir said. So do you have any more questions? Anyone? Feel free to ask in the chat or here.
I also just wanted to say that there is code available to try out the work. We provide a comfortable Google Colab, so you don't need to install anything. Just open a Google Colab and run it. You can see the link in Uri's post if anyone wants to try it out.
So I will share it again here in the chat if you missed it. So here you can see the link and the entire abstract of all the lectures. And also here we'll upload the slides and the recording. So this is a great place to catch up later on. And we will send it in our newsletter, in our Telegram. We'll publish it in the Facebook group. So that's it, I guess. Thank you all for joining.
I just have a last question to share. I just wanted to ask how long it takes.
Speakers, fantastic.
Sorry, how long it took you to train the self-supervision model?
So just to emphasize, in this work we did not train it. We took a pre-trained model. That was like that was like the message. Someone else, actually someone from Facebook, a very impressive group, they trained a very heavy, very time-consuming, very computationally expensive model. They trained it for their purposes. And then we took this pre-trained model and we simply did some analysis and tried to do some investigation of what signals we can find in it, what the representations are showing us. And once we discovered that the representations are both shared across objects and are differentiate different parts, then it was immediate which applications we can solve with them in a near state-of-the-art or state-of-the-art manner. So that's like the entire
Great. Thanks.
Perfect. So that's it, right? We don't have any more questions in the chat. So thank you all. As I said, we will upload it as soon as possible to our YouTube. And that's it. Thank you all. Take care. Bye-bye.
Thanks.
Thank you.
Bye.
Bye.
תודה רבה, להתראות.
ביי ביי, להתראות.